Hello, and welcome to Pictures of Numbers Dancing, the show in which we take a bit of mathematics, observe how the numbers within it are doing a dance, and attempt to capture those movements in a way that produces beautiful and compelling images. I'm your host, Tony, and you're watching the channel Tony Talks About Math. On this episode of Pictures of Numbers Dancing, we will be looking at a popular bit of mathematics called the Fibonacci sequence. You may have seen this before. It's a list of numbers that traditionally begins with a 0 and a 1, and then it goes on from there. And I'm listing a few terms in the sequence, and I'll tell you in a minute how these terms are generated. It's pretty straightforward. But I'm not here to talk about the mathematics of the Fibonacci sequence today. You can find plenty of videos that do that. Instead, I want to talk about how can we take a seemingly dry list of numbers such as this and use it to produce an image such as this. That's right, we're going to see how can the Fibonacci sequence lead numbers in a square dance. So to tell this story, I think the best way is to start by telling you how I came up with this idea in the first place. So let me tell you about young me. I was in school, I was a teenager, and I was doodling in the margin of a notebook that I had. It wasn't even a math notebook. It was a notebook, I think, from a Greek class that I was taking. I was studying Greek, and my handwriting wasn't perhaps the best, but anyway, in the margin of this notebook, I was doodling the Fibonacci sequence. So I wrote down 0 and I wrote down 1, and then you add those two numbers to get the next number in the sequence. 0 plus 1 is 1, so the next number is a 1, and then you add those and you get a 2, and so the next number is a 2. And to be clear, we're only adding two numbers at a time, so 1 plus 2, and draw a box just to make it really clear, is 3, and so we have a 3 next, and then 2 plus 3 is 5, and 3 plus 5 is 8, and 5 plus 8 is 13, and now I'm only writing down one digit for each number because I was working in the margin of a notebook and I didn't want my numbers growing to the left because they were going to bump into stuff that was already on the page. And a neat thing about addition is that you only need the last digit in order to find out what the last digit's going to be. So when we see the 7 and 4 and 1, it just means something ending in a 7 plus something ending in a 4 equals something ending in a 1. It doesn't matter that this number ending in a 1 happens to be 4,181. We don't even care. Point is, it ends in a 1. And the next number is going to end in a 5. And then 1 plus 5 is 6. And 5 plus 6 is 1. See what I did there? 5 plus 6 is 11. But we ignore everything but the units digit, so it might as well be 1. 6 plus 1 is 7. 1 plus 7 is 8. 7 plus 8 is 5. There, I did it again. So anyway, you keep doing this. And as I was writing these numbers down, I was sort of fascinated, wondering, is this going to be one of those things like an irrational numbers decimal expansion where it just keeps going without any pattern, and it's just endless variety forever? And then I realized, no, that can't happen because each digit only depends on the two previous digits, and at some point we're going to see the same two digits again. So right here, 1 plus 0 is 1. And so that means the next thing to write down would be a 1, and then we're going to have a 0 followed by a 1, which is how we started the list. So the 0 at the end might as well be the 0 at the beginning, because after this, we're just going to see the same thing again. It's just going to loop and repeat. And this kind of tells us that instead of thinking of this as a list of single digits, we should perhaps think of it as a list of pairs of digits. So the first pair of digits we saw was a 0 followed by a 1. So let me write 0, 1 as a pair. And then the next pair is 1 followed by a 1, and then a 1 followed by a 2, and then a 2 followed by a 3. And just to be clear, the rule for getting the new pair from the last one is the second digit in the pair becomes the first digit of the new pair. So we're going to have a 3 here. And the second digit in the new pair is produced by adding the 2 digits from the previous pair. So 2 plus 3 is 5. So that's going to be our next pair. And then we kind of keep going from there. 5, 8, 8, 3, 3, 1, etc., etc. And I'll just fill these in quickly. And we have this list of pairs now. And then we can ask a question like, well, is that all? Is that all the pairs that are possible? Have we seen everything? And the answer is clearly no, we haven't. So for example, nowhere in this list did we see the pair 0, 0. Because if we had, then the next pair after it would also be 0, 0, because 0 plus 0 is 0. A number ending in 0 plus a number ending in 0 gives you another number ending in 0. For a similar reason, we never in this list saw a pair that consisted of 2 even digits. Because if you have an even digit followed by another even digit, then the next pair after that is also going to be even, because even plus even equals even. So that's another thing that's missing. And then if you look carefully, you realize that there are even other things missing. For example, nowhere in this list do you see the pair 1, 3. So why is 1, 3 not in this list? Well, I don't know, it just didn't come up when we were adding and making our list. So there's a lot going on here. It seems like maybe we should get a bit more organized. So let's turn to a clean page in the notebook. And what we're doing is what mathematicians call working modulo 10, when we just look at the last digit of a number. I'm not going to get into the details of exactly what that means, but that's the word for it. And here's the sequence of numbers that we wrote down at first. I've written it a bit more compactly this time. Now, we mentioned that there's a 0, 0 that we didn't see, and there's not really much more to this list, because if I keep writing digits after 0, 0, they're all just going to be 0. So let's move on to the idea of 2 even digits in a row. So the simplest place to start for that would be 0, 2, and then we can generate a list off of that. So 0 plus 2 is 2, and 2 plus 2 is 4, 2 plus 4 is 6, and we can kind of keep going in this way. And we're going to start repeating more quickly than before because there are fewer options for even digits. So here we've reached 2, 0, and the next thing is going to be 0, 2, and that's where we started. Now we can also think about a sequence that begins with 1 and 3, because we noticed that we hadn't seen that. And 1 plus 3 is 4, and etc. So we get a list like this, and it's not very long before it repeats. There's only a few digits there. If I say a few digits, I mean there are only a few pairs, because we're really considering the pairs 1, 3, 3, 4, 4, 7, all the way to the end with 2, 1, and then 1, 3 comes after that. So anyway, if we want to think about these pairs of digits and think, well, have we seen them all now? Are we done? A good way to do this is to go into 2 dimensions and make a grid. So here's a 10 by 10 grid. And we can number each row in the grid 0 through 9 and say that those numbers represent the first digit in each pair. And then we can number the columns 0 through 9 and say those numbers will represent the second digit in a pair. So looking, for example, at our first sequence of numbers, the long sequence that we started with, it begins with 0, 1. And I've colored these brown, so I'm color coding these sequences because we have more than one of them. And I just chose brown for this first one, so I'm going to color the square 0, 1 brown to match that pair of numbers. Then the next pair is 1, 1, so let's color that as well. And then we have 1, 2, and we fill that in. And then we have 2, 3, and we fill that in. And we can keep going like this. Here's 3, 5, and 5, 8, and 8, 3. And as we keep filling these in, we start drawing a picture. So I remember the first time I was doing this, I was fascinated, wondering, what is this picture that I'm drawing? Like, what is it going to look like when I get to the end of the list, and at the time I really fancied the idea that it was going to be some sort of message for me from the aliens, and my interests have changed a bit since I was a teenager, but I still really enjoy the pattern that comes out of this, because after you fill the whole thing in, it turns into what I think is a fairly pretty picture that looks a bit like this. So here's the whole thing. I think it actually looks even nicer if you take this picture and shrink it down and then make another copy of it and another copy and another copy and stick all these together, and you see that it actually tiles nicely with itself and you get a sort of continuing pattern. So this is something that if these were tiles on a bathroom floor, for example, I would cheerfully stare at them for a while. I think it's an appealing pattern. Anyway, let's go back to our blank grid and consider that we have other lists besides the brown list that we haven't looked at. So there's this very short list consisting of 0, 0, and I'll just color code that one black and color this one square in the corner black, and I guess there's nothing very illuminating about that picture, so we'll just move on. And the next list that begins with 0, 2, I've chosen light green for this one. So let's make a light green square, and then we can sort of fill the rest of these in with light green. And we see that the light green squares are keeping a bit of a distance from each other because all the digits are even, and so they have to sort of stay 2 apart from each other, and there they all are. And by looking at this, you realize that we haven't quite filled in all of the even squares. So besides 0, 0, which we already know about, we're missing, for example, the square in row 2, column 6. So that tells us there's a list we haven't made yet. So going back to the notebook paper, let's write down 2, 6 and see what happens. 2 plus 6 is 8, and 6 plus 8 is 4 when we're working modulo 10. And 8 plus 4 is 2, and then we're done because 4 plus 2 is 6, and then we would start over. So we'll color that one in a minute, but first let's go to our 1, 3 sequence. So we'll blank out our square here, and let's choose dark green for this sequence. We used light green, so let's go with dark green. And there's 1, 3, and there's 3, 4, and 4, 7, and 7, 1, and we keep going. And there are only 12 squares to color in this time, and so there they are, and that's kind of a nice little pattern. You see 4 groups of 3 squares. It's like 4 little triangles or something like that. And then we can move on and say, well, what about our new little list starting with 2, 6? Well, I'd choose red for this one, so 2, 6 will be colored red. And then we have 6, 8, and 8, 4, and 4, 2, and there are 4 red squares. Now, again, we can ask, is this all? Have we found all of the squares that there are to color in? And so we can see this by counting. There were 4 of these, and there were 12 dark green squares and 20 light green squares, 1 black square up in the corner, and 60 brown squares. Now, if we add all those numbers up, which is to say, if we pile all these patterns together, it only adds up to 97, and we can see there are 3 squares left over that are not colored in, and we can see quickly which ones they are. There's a 0, 5, and a 5, 0, and a 5, 5. So we write down that sequence, and let's just go ahead and give it a color. How about purple? And so there we have a purple sequence and some purple squares, and there are 3 of those, and now that adds up to 100. So that's wonderful. Now, I find this image less appealing than the one that we had a few minutes ago, to be honest. We can still do the thing where we tile it with itself, and there it is, but I'm just less drawn to staring at bathroom tiles that look like this. I think part of the reason is the color palette that I've chosen, and I know that some people are better at choosing colors than I am. It's not really, I'm more of a mathematician than a colors guy. I don't know what to say. And you might be able to pick a color palette that makes this pattern a lot more appealing. But I think another reason that this one isn't that great is because the number 10 is a little bit clunky, and there's no reason we have to be working modulo 10. We can work modulo any number we like. So just for example, let's pick another number. How about 5? So if we're working modulo 5, we're going to get a whole different list of sequences. I'll show you how this works. Let's start out with the simplest possible one. 0, 0 is still the 0, 0 sequence. There's not much to it. There's one pair in the sequence, and if we make a grid, it's going to be the top left corner. We'll just color it black, and that's that. Now we can also start a sequence of 0, 1, and let's see how modulo 5 addition works. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 0, because modulo 5 means treat 5 like it's 0. And since 2 plus 3 is 5, we call it 0. The biggest number we're going to see here will be a 4. So 3 plus 0 is 3, and 3 plus 3 comes next, and that would normally be 6, but 6 is 1 more than 5, so we call it 1. 3 plus 1 is 4, 1 plus 4 is 0, and then we get a 4 and another 4, and 4 plus 4 is 3, because it's 8, which is 3 more than 5. And then we can keep going like this, and we get a list of numbers, and it amounts to 20 different pairs. Now, 1 plus 20 is only 21, so we must be missing something. And just like previously, we don't see a 1 followed by a 3 anywhere. So let's start with 1, 3 and see what we get that way. 1 plus 3 is 4, and 3 plus 4 is 2, modulo 5, right? 4 plus 2 is 1, 2 plus 1 is 3, and that would be repeating, so we've got our 4 pairs that we're going to see here. And now these numbers all add up to 25, so we're done. Now if we take our longer list with 20 pairs and color it green, then we get this picture. And if we take our shorter list with 4 pairs and color it red, we get this picture. And yes, these are exactly the greens and the reds that we saw in our modulo 10 grid. If you take the lists on this page and multiply each number in them by 2, then you're going to get the green and red lists from the previous page where we were working modulo 10. Since 5 is a prime number, it doesn't have any divisors other than 1, which is responsible for the black square up in the corner. So, while 10 has all the patterns for 5 sort of built into it, 5 really only has its own thing. I think it's a little more pure and a little nicer looking due to that. So I think the prime numbers work a little more nicely here. And we can take this and tile it and have a few copies. Here's a 3x3 set of our 5 grid, and again, this is a reasonable enough tiling pattern. I would stare at this if I were sitting in a room and this were on the wall or the floor. I think it's a fairly nice tiling. Now there's something we can do with a number like 5. Since it's an odd number, we can stick our 0 square right in the middle, because there is a middle. With an even number, there's not a center square, but with an odd number, we have a center square. So we can put 0 there, and we've just sort of shifted everything over. And then our green squares look like this, and our red squares look like this, and when we tile the whole thing, it looks like this. This isn't super different from the pattern we saw before, but I think there's something nice about having the black squares centered. We can play a similar game with any number, and I think the nicest pictures come from the odd prime numbers. So for example, if we work modulo 7, we get a picture like this. As you can see, there's the 0, 0 black square up in the corner, and 7 times 7 is 49, so there are 49 squares. one of those black, and of the 48 remaining squares, we have 16 maroon, 16 blue, and 16 yellow. Each of them makes up their own pattern, and if you look at this thing tiled several times, then you can see that the maroon squares are doing this sort of pinwheel pattern, and the blue squares have this little thing with sort of triangular shapes and dots, and the yellow squares have some things that look like Tetris pieces, and each one sort of makes an appealing picture. We can also take this pattern modulo 7 and center the 0. And I've chosen a different color palette this time just because I don't know how to choose color palettes, so I just try lots of things and see what looks good. And if you take this one and tile it, you get the picture that I showed you at the beginning of the video, and I promised to show you how we would get from the Fibonacci sequence to this picture. So I hope you find this interesting. I hope you think that this is a neat way to make pictures. I encourage you to play around with this. Pick a number, write down a sequence, draw a grid, pick some colors, and see what kind of picture you get. And if someone catches you doing this and sees you writing down lists of numbers and drawing grids on a piece of paper and asks you, "What are you doing?" or "Are you doing math just for fun?" you can say, "Kind of, but I'm also doing art. I'm looking at pictures of numbers dancing." And see what they say. I hope that you have some fun with this. I hope that you find playing with numbers in this way to be kind of appealing and interesting. I hope you like the pictures that come out of this. And I hope to see you next time on the next episode of Pictures of Numbers Dancing. Please let me know what you think in the comments. If you enjoyed this, please click on like and subscribe. And thanks for watching.